Everyone. We're going to be talking about that explicit definition today and exploring how we can make explicit definitions for both arithmetic and geometric sequences. So, an explicit definition is a formula that determines the value of any term in a sequence using the term number. An explicit definition of a sequence can be written as an expression or in words. And we're going to look at two situations here. The first one that we see is Julian's family is 250 miles away from home. So that's that starting value, how far they are from home. And they drive 50 miles towards their home every n hours. So we start with our 250 and we're figuring out how far we are from home. So we're going to do subtracting because we're getting closer and closer to home. 50 times the amount of hours, n. So for 1 hour, they're 50 miles closer. After 2 hours, there's 100 miles closer, and so forth. 250 represents the starting distance. Minus 50 represents the distance traveled each hour. Negative 50, because they're getting 50 miles closer to home. And negative 50n represents the total distance that they've traveled, and n is the number of hours driven. So if we wanted to figure out the after 4 hours, we could plug in n for 4, and we do 50 times 4. 50 times 4 is 200, and 250 minus 200 is 50. So the sequence term number after 4 hours is 50. So it's nice and easy. We don't have to figure out what the second, third, and then fourth is. We can just plug a value in and figure out what that term number is. So that's an arithmetic sequence, addition or subtraction. On the right, we have a scientist tracks a group of 250 bugs. And it says each month, the number of bugs is 1.5 times more for n months. So we're doing a geometric sequence. We see our multiplication. 250 represents the initial amount of bugs, and then we're going to multiply it by 1.5, which is the ratio that the bugs grow each month. That's our multiplier. And we're going to raise it to the nth power, and that's going to represent the number of months. So if we wanted to see after 3 months, we could do 250 times 1.5 to the third, which in our calculator gets us 843.75. So that's just an example of plugging in that value of 3 and seeing it went from 250 to 843. So we can see that growth. So that's the little lesson summary. We're going to do practice with this on the next slides. So here's slide 2. Jamar had 80 followers on social media. His numbers of followers tripled every month for 4 months. Select all the expressions that represent Jamar's followers after 4 months. So we're starting with our initial value, which is 80, and they're tripling, right? So we're multiplying by 3, and we're doing that for 4 months. So we're going to do times 3, times 3, times 3, times 3, 4 times. Another way to write this is when we have 3 multiplied by itself 4 times, this is 3 to the 4th power. So we have 80 times 3 to the 4th power. So those are the two ways that we can represent this expression for after 4 months. Once you're all set, push ahead to slide 3. Problem 2. The weather forecast predicts a snowfall rate of 0.75 inches of snow per hour overnight. There are already 9 inches of snow on the ground in Anushka's neighborhood. Complete the table to show the amount of snow on the ground in inches after n hours. So when at 0 hours before the snow starts, we already have 9 inches of snow. Now, it tells us that it is 0.75 inches of snow per hour. So 0.75 inches per hour. So we're adding 0.75 each term. So this is an arithmetic sequence with a constant difference because we're using addition. 9 plus 0.75 is 9.75. 9.75 plus 0.75, or did I type that wrong? Oops, plus 0.75 is 10.5. Add another 0.75 to get 11.25. And if we keep going, we can use our little formula over here. So we had 9, and then, oops, we are going to add 0.75 times n. So now if we want to find the 8th hour, we're doing 9 plus 0.75 times 8. So 0.75 times 8 gets us 6. So 9 plus 6 is 15. So our last one for 8 hours is going to be 15 inches. Beautiful. Once you have everything you need, push ahead to slide 4. The population of a city was 100,000 in 1970, and it has doubled 3 times since then. Select all the expressions that represent the population today. So we're starting with 100,000, and it's doubling. So it's going to be a geometric sequence with a constant ratio. The constant ratio is 3, and we're raising that to the nth power. We're looking specifically, oh wait, sorry, hold on, it's doubled. So it's 2 to the n. There we go. We're looking specifically for 3 times since then. So we have 100,000 times 2 times 2 times 2, 3 of them, because our n value equals 3. So that is here. 2 times 2 times 2 can be also written as to the 3rd power. These are equivalent expressions because we have 2 and we're multiplying it 3 times. And we could also type all this into a calculator. 100,000 times 2 cubed is 800,000. So our answer is also 800,000. And we got that just from doubling it 3 times. Beautiful. Push ahead to slide 5 when you're ready. Problems 4 and 5, it says, here's a table representing a pattern. Choose the equation that represents the table. So first of all, we notice that we start with a 60 for our term 0, which is our starting term. So they all start with 60. So that's good. We can check that off. Now we need to look at how this is changing. So if it was arithmetic, this would be subtracting 30. And then if we subtract 30 again, we would get 0, which is not the number that we have here. We have a 15. So it's not going to be arithmetic, which means it must be geometric. So we can cancel out this one and this one because that has addition and subtraction. Those are arithmetic sequences. 60 to 30, we're multiplying by a half or dividing by 2. Half of 30 is 15. Half of 15 is 7.5. Half of 7.5 is 3.75. So we see that our common ratio is 1/2. So we're going to select that option. And I want you to take some time to fill in the explain your thinking. What are the key principles that we pointed out to get us to that option? Pause the video if you need to, and then when you're all set, push ahead to slide 6. Maya earns money by shoveling snow in her neighborhood. She starts the winter with $52 in her bank account, and she'll deposit $10 for every driveway that she shovels. So we have our starting value of 52. Every time we're depositing $10. So we're adding $10 each time. So this is arithmetic with a common difference, which is plus 10. 52 plus 10 is 62. 62 plus 10 is 72. And 72 plus 10 is 82. So we see that that pattern is just boop, going up each time by plus 10. Perfect. Push ahead to slide 7. Oops, there we go. So same thing, we had 62, 72, 82. This is the same snow shoveling problem. Here's your table from the previous screen. Write an explicit expression that represents this situation. So we always want to do our starting value plus the constant difference times n. So our starting value here is 52. Our constant difference is a positive 10. And then we're going to put n. And we can hit submit. Beautiful. Slide 8. A group of students tracked the number of likes on a social media post. They represented this number using the equation n equals 40 times 1.5 raised to the t. And n is the total number of likes, and t is the number of days since the students started counting. So in this scenario, what does 40 mean, and what does 1.5 mean? So I want you to take a little thought about that and think about what could 40 mean, and what could that 1.5 represent? How did we put those numbers there? What do those spots represent? When you're all set with that, push to slide 9, which is continuing this similar problem, but it says how many likes do the students predict there will be 2 days after starting the account. So we have n equals 40 times 1.5 to the t. To figure out after 2 days, we're just plugging in 2 for t. When we do that, 1.5 squared is 2.25. So n equals 40 times 2.25, which gets us 90. So we started with that 40 likes, and now after 2 days, we are at 90. I don't know why it says squirrels. That's really silly. But yeah, it's going to be 90 likes. Beautiful. And then spiral review. So write this using an exponent. So just as a reminder, when we're working through exponents, what we're multiplying every time here is 4/5. How many times are we multiplying that? 1, 2, 3. So this is 4/5 to the 3rd power. Problem 11, similar. How would we write this using an exponent? And then problem 12, I want you to think about finding that 100th term. And then you can see the reflection letting you know if they're correct on slide 13. Reach out to me if you have any questions or you need support. Y'all got this. Bye, friends.